Now, what is the molecular reason for the observation of char-gas rules? Why does A pair with T in DNA and G pair with C? So on the left, we see we are looking at one nucleotide of a larger nucleic acid, okay? And we'll call it this one here, all right? So there's something connected on the 5' to 3' end. At the 5' end is a C nucleic acid, so C's up here. Right, the squiggly line just shows that all I'm showing is a simplified version of this where we can't see the 5' end nucleotide and the 3' end nucleotide. But for the 5' end, this would be C. For the 3' end, this would be T down here, okay? But we're focusing in just on the adenosine because we want to look at why A would specifically bind with T. And so here's the structure of adenosine, here's the nitrogenous base. So the complementarity all has to do with the nitrogenous base, because remember, all of these, for all of these nucleotides, the ribose, the deoxyribose ring is going to be the same, and the phosphodiester is going to be the same for the linkages between these. What differentiates these is what's happening at the nitrogenous base component of this. So here's the adenosine, and then if we look at thymine, use this. And I'm just going to draw the nitrogenous base here. Here's thymine. Actually, I'm going to rotate this just a little bit so it's a little easier to see. Okay. Here are nitrogens. All right, remember, this is going to go to the ribose. Let's try that again. This is going to go to the ribose ring. All right, here are nitrogens on our 6-membered ring. And then this is going to be an H. This is going to be a carboxyl, okay? Now look at the pairing. Look at the complementarity of the different hydrogen bond donors and acceptors between the adenosine and thymidine. Okay, so on the adenosine, there's an H bond donor here and an H bond acceptor here. On the thymidine, it's in the corresponding positions, it's reversed. There's an H bond donor at this position and an H bond acceptor at this position. And so the hydrogen bond donors and acceptors between these two complement each other. So this forms a hydrogen bond between adenine, between the carboxyl group of thymidine and the amine group of adenosine. And then this in-ring nitrogen is the hydrogen bond acceptor for the hydrogen on the NH group of the thymidine ring. Okay, and so it's this complementarity between the hydrogen bond donors and the acceptors that allows for these to selectively base pair with each other. So we call this, again, base pairing. Okay, and the canonical A to T and G to C base pairs that we see from char-gas rules are called Watson-Crick base pairs. Now, try to draw the structure then. Try to draw the hydrogen bond interactions for the GC base pairs on your own and convince yourself that that is going to be complementarity as well. The hydrogen bond donors and the hydrogen bond acceptors for these two are also going to be complementary.